Hi, and welcome to Module 10 in the first video lecture. This is the last module in the first video lecture, and it is on proofs. Now, the topic of proofs is a broad one. We're not going to cover almost anything, strictly speaking, but the goal of this is to get you the ability to look at a paper that involves proofs and have some idea what's going on in the paper. You need more sort of stuff to do proofs by yourself, but again, that kind of information, that kind of knowledge comes in later classes you might take. Here, we're just trying to get you to the point where you can look at a paper that has a proof in it and know what's going on. I'm again violating my rule of not having set slides. This slide is a list of definitions that we're going to go through and make sure we understand them all. Okay. So the first few are definitions based on definitions related to proofs and what goes into making a proof. The first is assumption. All theories and propositions and statements we make in life in general, and also in political and social sciences, have underneath them certain assumptions we're making. Typically, we don't actually state our assumptions. They're implicit in our discourse, which can often lead to actually some difficulties in communications when assumptions are not shared. In the case of game theory and formal theory more generally, one of the things it does is make explicit all assumptions as much as possible, with the goal of understanding what assumptions are necessary in order to derive certain outcomes. So oftentimes in a paper that involves game theory, for instance, or in some kind of statistical proof, you might see starting off with assumptions. Assumptions underlie the use of certain statistical models, and assumptions underlie all models you might make in game theory. Assumptions are just what they mean in English. They're things you assume to be true. You might also sometimes see the word axioms. Generally, axioms doesn't usually come up very often, but axioms generally mean the same thing as assumptions. They're things you assume at the beginning of the process. They're stuff that are just taken for granted. It is always good, whether you in formal theory, game theory, or if you're writing up your ideas, or just talking, it's always good to make clear your assumptions ahead of time. These assumptions are used then to derive implications of them. And formal mathematical language has several different kinds of implications, different words for them. We'll do a couple here. There are more out there. A lemma, which is an odd word you probably haven't heard before. A lemma is like a small theory, a small theorem, a small proposition. It's a thing that is not in and of itself interesting, but is interesting only in that it helps you prove more useful things later. So you might see that in the course of proving a more complicated theorem. Theorems and propositions, which are often used interchangeably in political science and formal theory, are interesting statements. They're statements that you have deduced from a series of assumptions in some fashion, and they are statements of logic that are true. You have derived them as being true from a set of assumptions. They're true given these assumptions. And they're called propositions or theorems because they're interesting to you in the context of what you're trying to say. A corollary is a statement that follows directly from a proposition or theorem. What does follows directly mean? Well, that relates to the next term, proof. In order to show the truth of a proposition or a theorem, or a lemma for that matter, you must offer a proof. Proof here, again, means just like it does in English. It's the proof that you are correct. Here, a logical proof is a set of statements that follow from assumptions that show the truth of the logical truth of your proposition or theorem or lemma. A corollary is something that follows so directly from a proposition or theorem or lemma that it does not need any further proof. So, for instance, if you have proved that the sky is blue, you do not need to subsequently prove that the sky is a color. Right? Blue is a color that follows directly. Okay. Now, the rest of this module is going to be devoted to a little discourse on how you might actually prove things. Right? All mathematical knowledge comes via proof or assumption. We assume things and then prove other things from those assumptions. Since a lot of the stuff we do will involve the derivatives, not necessarily a derivative, but the consequences of mathematical knowledge, it helps to understand how that knowledge was derived in the first place. The most basic implications are in two forms, well, three really. The first is a sufficient statement. A sufficient statement is a statement that it's an if statement. I guess the simplest way of saying it. Okay. It's an implication. So we often write implications like this. This symbol means implies. The equals with an arrow, with a greater than sign at the end of it. It looks like an arrow with a double line. That means it implies. If we have A implies B, well, we treat A and B as logical statements. For instance, A is I like to eat ice cream, and B might be I have eaten ice cream. That's not a true statement in this case. Liking it does not mean you have to eat it. But if we knew, for instance, so A implies B. That's how I read that. That's a sufficient statement. It means whenever A happens, that is sufficient for B to occur. So if A happens, then B happens as well. That's a sufficient statement. It is not, however, a necessary statement. Just because A makes B happen, just because A leads to B in a causal chain, right, a causal effect, A causes B, it does not mean that A is necessary to cause B. Other things might also cause B. We write that like this. The reverse statement is a necessary statement, and it's the reverse of the implies sign. The implication goes the other way. If B is sufficient for A, right? This is B is sufficient for A, or A happens only if B happens. I'm sorry, I apologize. B happens only if A happens. I always get this mixed up when I say it out loud. B happens only if A happens. How does that work? Well, and this is the trickier one of these things. A happens only if B happens. Therefore, A is necessary for B to happen. Why is that? Well, if B implies A, you look at it sort of in reverse. If B implies A, then whenever B happens, A also happens. Therefore, we never observe B happening without also observing A happening, because B is sufficient to imply A. So again, whenever you see B, you also see A. Therefore, A always happens when B happens, and therefore you don't see B without also seeing A. In that sense, A is necessary for B to happen, because you can't get B without also getting A. Just take a second, think about that. Necessary is one of the more complicated logical ways of thinking, I think, that people learn the first time, and it's an important one. Necessary means you must have it be true in order to have the other statement happen. That makes decent sense in English. Logically, it means that whenever B happens, A also happens. A must be necessary for B, and we can write that like this. Only if is another way of saying this. B happens only if A happens as well. So in the first statement, it's B happens if A happens. Right, so here's the first statement here. This is the if. B happens if A happens. Second one, which is the only if. B happens only if A happens. Those are logical implications, and those are what we deal with in all science. We're trying to understand the cause of things, how one thing A causes another thing B. A common argument in political science and international relations relates to the theory of democratic peace. If you have two democracies, they don't fight. That's sort of a theory. How does that work here? Well, it means it's an if. If you have two democracies, then they have peace. It is not necessary. You can have peace without having two democracies. That's important. It's a sufficient statement. And there's an argument about that, but we'll assume for the sake of this argument that it's sufficient. But it's not necessary. Okay. What if you have both necessary and sufficient? Well, if one thing is both sufficient to get the other thing and necessary to get it, then they always only occur at the same time, together. In some senses, they're equivalent statements because they only ever occur together. You can write that like this. You put the sufficient thing over here, the implies, but the implication goes in both directions. That's also read as if and only if, or occasionally IFF for if and only if. That IFF is over here. So A implies B and B implies A. A is necessary and sufficient for B, and vice versa. That's the strongest kind of implication because it means these two statements are basically the same thing. And most of what we do in trying to understand, in trying to prove things, is create chains of implications just like this in order to understand how one thing might cause another. Okay. So that's the basic stuff. Now let's talk about logic a little bit. Logic is a very broad topic. We're obviously not going to cover a whole course on logic in the next 5 to 10 minutes or so. So what we're going to focus on is just the bare minimum that you might see in looking at political science proofs and social science proofs in general. The two sort of core ideas of logic besides the implications we just dealt with are the logical statements and or. And is often written like this. And or is often written like this. So this would be and this would be or. These should look pretty similar to the set notation we did before. The and looks kind of like an intersection. And the reason for that is because if you view a set, two sets as statements, the intersection of those statements is when they both occur. If A is true and B is true, that's the intersection of those two sets corresponding to statements. So the caret here, the and, looks kind of like an implication. Looks like an intersection. The or happens when either is true, so that's the union of both sets. So it looks like a union sign. And or. We create compound statements by adding statements with and or. So for instance, this means A and B are both true, whereas this means C or D are both true. And means you must have both statements true for the overall statement to be true, and or means you must have either statement, one or the other, or both. There are other logical statements out there. If you study computer science, you'll deal with a bunch of these, or obviously math or philosophy. But these are the ones that primarily show up in political science, and they relate to compound statements. We can manipulate them a little bit using some other stuff. I'll skip down to negation for a second. Negation, I showed this before for not. It's kind of like that, or sometimes you see this. It means not. So if A is a statement, that means I like ice cream. That's read not A. Not A means I don't like ice cream. If you combine not A with A, you have everything, right? We're going to assume, by and large, that things can either be A or not A, right? There's no in between. De Morgan's laws let you play around with negation. So if you have the statement A and B, and you negate that, so now it's not A and B. Well, how can you not have both be true? Well, you could have if not A is true, then that's not true. Then A and B is not true. And if not B is true, or if not B is true, that's not true. So this is the same as this. Not A and B means not A or not B. If one of A or B isn't true, then the and is also not true. You can also do the reverse one. In order for A or B to be not true, you need both A to be not true and B to be not true. So those are the two of De Morgan's laws, and they help you use ands correctly. Okay. The only other one I want to mention before we move on, well, two more I want to mention before we move on. One is the converse of a statement. If this is the statement you're trying to prove, the converse is with them flipped. That's the converse. A implies B has a converse, B implies A. The converse is not always true. It may be true, it may not be true, but it is not automatically implied by the statement itself. Just because A implies B does not mean B implies A. For instance, if I have 2 pennies, that implies I have less than 5 pennies. If I have less than 5 pennies, it does not imply I have 2. I could have 1, I could have 3, I could have 0, and so on. The converse is not automatically implied by the statement itself. However, there's another statement we could do, the contrapositive. Again, go back to the original statement. The contrapositive is taken by taking the converse and negating both sides. Not B does imply not A. If I have 2 pennies, I have less than 5 pennies. If I don't have less than 5 pennies, I can't have 2 pennies. Right? Because I have more than 5 pennies, which does not include the number 2. The contrapositive always follows directly from the original statement. It's identical to that statement. So when we're proving things, we can prove the contrapositive or the statement itself, whatever's easier. Okay. And that takes us to proofs, the last sort of topic here. I've listed some ways of proving things at the very bottom of this slide. These are not exhaustive in the slightest. They're just a small listing of proofs that are reasonably common. You might see reasonably commonly in political science. So a direct proof is a proof in which you construct a chain of argument from assumptions to conclusions, to the conclusion you want. So if you're trying to prove that A implies B, you use a chain of arguments to get from A to B. There are techniques for doing this that you'll learn in other classes. Here we're just trying to get you to recognize these. Okay. So let's give one sort of example. This is from the book. How do we prove that multiplying that adding 2 numbers gives you an even number? Okay. Well, how do we do that? Well, let's see. Actually, yeah, no, 2 even numbers are even numbers. So how do we do that? Well, how do we define an even number? An even number is any number that has this property. If x is even, then x equals 2y for some y. Right? So if x is even, then it's a multiple of 2. Right? That's the definition of even. Well, let's say x and y are both even. So we want to show that if x, y are even, then x plus y are even. This is a common for the first proof. How do we do that? Well, let's write x equals 2k and y equals 2l. We can do that because they're both even. Then x plus y equals 2k plus 2l. Now what do we do? Well, that implies that x plus y equals 2 times k plus l by the distributive property. Numbers, real number. We're assuming x and y are real numbers. Well, k plus l is another number. Let's call it m. But now we've said x plus y is equal to 2 times another number, which means x plus y is even by definition, and we're done. So we can write a little box at the end, or we could say QED, quod erat demonstratum. It means we're done with the proof. We've proved what we wanted to prove. We've started from our assumptions, which are x and y are even, and we've used a chain of arguments to get to the fact that x plus y are even as well. And in between, we've used steps that are related to things we know already. We can always use steps in our proof that we know already from other things. Here we use the distributive property of real numbers, which is an assumption of the real number line. Okay, that's a general direct proof. We directly prove the conclusion from our assumptions. There are other proofs as well. A proof by construction is often useful if you want to show something exists. One way of showing it exists is to actually give an example of it. So you construct an example that matches what you're trying to show, and you've shown it exists. That's reasonably common in game theory when you're trying to show a particular equilibrium exists. You just find one. Proofs by exhaustion are not when you get exhausted trying to prove things. A proof by exhaustion is when you have many cases, when you break your problem into many cases, and you prove it's true for every single case. This happens a bunch in game theory when you have a parameter space, a space of all parameters. We'll talk about that more later in the course, in these video lectures. You have a parameter space, and you show that it's true for this little area, and this little area, and this little area, and so on until you have all the areas shown. It's a proof by exhaustion. A proof by induction is a funny sort of thing. It comes up when you have some kind of series. Now we'll talk about series and sequences very shortly in the next set of video lectures. But one way of doing this, just to show you how this works, say we wanted to show that, this is also from the book, say we wanted to show that the sum, remember this is a summation sign, the sum of I from 1 to n, so we're adding 1 plus 2 plus 3 plus 4 plus 5 and so on, equals this. This is occasionally useful to understand how to add sums. For instance, let's say I want to take a sum of I from 1 to 10. Well, I can plug in 10 times 11. That's 110. Divided by 2 is 55. That's the sum of I from 1 to 10. How do we show this? A proof by induction is a good way to show proofs that involve series of things, or sequences of things, and they have 3 steps. First, you assume the base case. The base case is the first case here. Here is 1. So we show that for n equals 1, this is true. Well, for n equals 1, 1 equals 1 times 1 plus 1 over 2 equals 1. So 1 equals 1, the base case is true. We've shown the base case. Now we assume what's called the inductive hypothesis. The inductive hypothesis is that this is in fact true. We're assuming the answer in a sense. So to assume the inductive hypothesis, that's step 2. Step 3 is the inductive step. Now we show this is also true for n plus 1. So let's take it again. So we're trying to show, so now we go plus 1. Well, how do we do that? If this is actually true, then we have, so this equals the sum from 1 to n plus n plus 1. So it's the sum of 1 to n plus the new one we just added. Let's see. This thing we've assumed to be equal to that. That's the inductive assumption, the inductive hypothesis, plus n plus 1. Now we can do some algebra. We can take n plus 1 out of both of these, right? Because, first we can multiply the second one by 2 over 2. So let's do that over here. 2 over 2 is 1, so remember we can always multiply by 1. Now they're both the same denominator, so we can add them. That gets us this. Over 2. Now we have n plus 1 in both terms, so we can use the distributive property to get our final answer, which is n plus 1 times n plus 2 over 2. But if you look, if you change n plus 1 over here, call it m, then you have m times m plus 1 over 2, and that's exactly what we're trying to show. That's exactly what we assume to be true. So in fact, we've proven that by proof by induction, we've proven that the original statement up here is true. The base case was true. The inductive hypothesis we've assumed, and we show if we add one more, it is still true. Why does that work? Well, if it's true for 1, and we can always add 1 to whatever it's true for, right? So it's true for 1, and if we add 1, it's still true, then it's true for 2, and if we add 1, it's still true, so it's true for 3, and so on forever. So by induction, we've proven it to be true. So that's a common proof used for sequences in series. Now be really careful here. Induction can also mean an empirically driven hypothesis. We observe a lot of things and derive a hypothesis by induction from our observed data. That's a related thing in the sense that it involves repeated actions, right? But it's a different thing than this the deductive induction proof. Okay. So those are some varieties of direct proof. We can also have indirect proofs. The most common of these is the counterexample. In fact, I would wager that the most common proof of all types in political science, game theory, is the counterexample, proof by counterexample. And there's a sort of a common usage word, it's the exception that proves the rule. That is not true in logic. If there's an exception to the rule, it is not a rule. It's false, right? So if you want to say that A implies B, and I can find just one case in which that's not true, A does not imply B. So a common way of proving this is to show that it is not true. So if you want to show that A does not imply B, for instance, you just need one example of A not implying B. Kind of relatedly, you can also prove. So counterexample is one example which is not true. Contradiction is you can prove that the negation of the statement is also not true, right? So if you prove that not A implies B is false, then it must be true that A implies B. A double not means a yes, right? So in this case, two wrongs do make a right in the sense that two falses together make it. If false, false together, they make it true. So if you have not A implies B, means the statement A implies B is false. If this statement is false, then A implies B. So again, sort of to be a little more clear about that, not A implies B is equivalent to A implies B. That's a proof by contradiction. You basically contradict your negated statement to show that the original statement is true. That's pretty common as well. I see maybe it's more common than counterexample. Counterexample, you find one example for which A does not imply B. And those are common ways. You can also show that you can also prove the contrapositive, which is sometimes viewed as an indirect proof. The contrapositive is the same as the statement itself, and therefore, if you prove the contrapositive, you've proven the statement. It's indirect in that fashion, but it's often accomplished via the methods of direct proof. So you can call it whatever you want, but that's another way of proving things. And again, there are lots more ways of proving things, but these are ones you'll commonly see. That's it. Thank you, and thank you for watching video lecture 1. The next video lecture will cover chapter 3 and 4 of the textbook, and that includes relations, functions, some more information about sets, and continuity and limits and sequences and series. That'll be broken up into multiple modules as well. And hope to see you there. Thank you very much.